Okay, welcome to Unit 2. We're going to start talking about motion, and we're going to talk about motion in one dimension. And that just means that it's like forward and back, up and down, left and right, in and out. Those are all examples of motion along a line. And so we're going to keep it very simple to start with, and then we will add to it as we go along. Okay. Each chapter and each unit that we start, we're going to have these things called need to knows. And this is the things that the items the district thinks that we should cover in making sure that you get the education that you're supposed to in physics. So we're going to describe motion, velocity and acceleration and how they're different, kinematic equations that are used to calculate displacement, time, velocity, and acceleration, vectors and how they can be useful, graphs used to illustrate motion in one dimension, and then free-falling bodies and their place in one-dimensional motion. These are the terms that we're going to cover, and I would just write them down in your notes, and that way as you get ready to study for your test, you can go back to these terms and just go through one at a time and say, yep, I know that one, and I know that one, and so forth, and use it as part of your review. So the terms are magnitude, frame of reference, acceleration, velocity, instantaneous velocity, average velocity, displacement, distance, speed, free fall, gravity, kinematics, vector, resultant vector, and scalar. Okay, so we're going to start with three basic definitions. A position is just where you are, and this can be a coordinate or a point, and we represent that by x. Displacement and distance in the normal way of speaking, so in everyday language, would be pretty much the same thing. But in physics, we've got to be very careful, and they do have a different meaning, so we have to make sure that we're really listening or reading what they want. So displacement is a change in position of an object between a final and initial point. We write that as delta x is equal to the x final, f, minus x initial, which is I. And then distance is just how far something has traveled. And you'll see very shortly what we mean by that. Okay, so here is a distance from school. And you can see that it starts here at the school, which I guess is the origin. So here we're going to start at the origin. And we're going to travel for about 10 minutes until we hit this point. And that is in 2 minutes, we've gone this distance. We've doubled that distance in 4 minutes and so forth. And so you can see that we are just traveling along at a constant speed. So this shows us that it's a constant speed. From this part, if you notice, our distance doesn't change, but our time keeps moving. So we must have stopped, maybe to look around or pick flowers or something like that, but we're not moving. From about 12 to about 14 minutes, it looks like, we moved, but look at the slope. This we've covered in that amount of time, we've covered a lot of distance, and so that must mean we traveled faster. Here we've stopped again for a certain amount of time. Okay, now we're headed back towards home, and so as we head back towards home, you can see that we're traveling at a constant speed. We rest, travel again, rest, and then race back to where we were going, back to school. So by looking at where things are on this graph, we can actually get quite a bit of information. So if we're only looking at one important characteristics, like we were talking about for distance, we were only saying how far did you go. When we have two important characteristics to follow, displacement, we not only want to know how far something is, but in what direction it is, because that's what's going to really help us out. Anything that has only one important characteristic we consider a scalar measurement, and if it has not only say how far the magnitude of something, then and it has direction, we call it a vector. So here are the basic definitions. So scalar, a physical quantity that has magnitude but no direction, and we talk about the absolute value of a number or the amount of it. And most of us know how to think about this when we hear about a magnitude, say 5 earthquake. We know that's kind of something you would notice, and it's probably going to do damage, and so we know that's how big the earthquake is. And so magnitude is how big or how measurable the number itself, the value it has. Whereas when we talk about a vector, we want to know the magnitude, but we also want to know its direction. So if I told you that in a room I hid a bag of coins, and the coins are worth $500, and I told you it was going to be 5 meters away. Well, that's great, but you don't know 5 meters from what? I need to tell you more. 5 meters to the left of the fire blanket, or something like that. So by giving you not only how far, the magnitude, as well as the direction, you could go find that bag of money if you needed to. So here's a practice question. So let's see how we do on answering this and make sure that we understand. So if I want the distance from A to B, that wasn't intentional. If I want the distance from A to B, I am just going to look. So it's about 5. It's off a little bit. So about 1 to 5. So that's going to be about 4 meters. I want the displacement from A to B, and it is 4 meters again, but it needs a direction. And so we're going to go ahead and say that it's going to be 4 meters, say, forward. Okay? And that can be a bunch of choices, but it's giving us a direction. The displacement, if now I go from B to A, is still the 4 meters, isn't it? The same distance, but because I'm going the other way, it would be backwards. I'm going back towards the origin. The displacement from A to E, remember we talked about displacement was the change in X, and so I want to know the X final minus the X initial, and that is going to be, my final was at 1, and I'm going to subtract from that my initial, which was also at 1 meter, my units in, and so my displacement is 0 because I started and stopped at the same place. But the distance from A to E, that's the absolute value, so I'm just going to add them together. So from 1 to 5 is going to be 4 meters for my first leg, A to B. For my B to C, I went back towards home for 2 meters, but it's an absolute value, so I'm going to go ahead and put 2. I then turned around and went away from the starting position, the origin, and so from 3 to 7, which is 4, and then I went from 7 all the way back to 1, which is 6 more, and these are all in meters, and so I'm going to end up with 16 meters as my distance, and that's how that works. Another thing we can think about is speed, which is just the rate of motion, distance divided by time, and velocity, which is rate of change in displacement, which is the displacement delta x divided by the time it takes to do that change. So let's look at these 2 questions and see if we can answer those. We drive at constant speed to Grandma's house for Thanksgiving dinner, and we're going to stay a while, so we're just going to draw a real quick graph, and we're going to put time and distance. So we're going to stay a while, and then we're going to turn home at the same speed. Well, I know if it's a constant speed, it's a straight line, so I'm going to go to Grandma's house. I'm going to have, it's supposed to be flat, I'm going to have some turkey dinner, and then I'm going to go back home so I can sleep in my own bed. And so it's going to have this shape with a flat top and the equal slopes, but in opposite directions, a positive and a negative slope on either side. Okay? Now we're going to be cruising along on a highway, and we see a policeman parked, I'm sure in plain sight, and we're going to see what it would look like as well. We're going to have the same parameters, time on the bottom on the X, distance on the Y, and so if I'm going a pretty good clip, the slope is going to be pretty steep. I see that policeman and I get back within the speed limit, and it's going to flatten out. It's supposed to be nice and flat, not curved, but there it goes. Okay, so prior to seeing the policeman and after seeing the policeman, and all it does is it changes the slope there. Okay, so go back to this, what we had talked about before. Only one important characteristic, the magnitude of the ratio between distance and time is speed. 2 important characteristics, we both have the distance and the time, but we also know the direction, which is bringing into this to the equation of the displacement, and then it goes back to our scalar and vector. Magnitude, but not worrying about direction, is scalar. If you have direction and magnitude, it's going to be a vector. Okay, so we just did that. If you want to go ahead and answer these again, that's great, but we just did that. So the next part I need you to do is, in your book, there are some practice questions that just are word problems that we get to apply what we just did. And so you'll go to your book and do the practice problems on page 44, and then you can come in and check them with me or check them with one of your friends because we've checked them in class. So good luck, and I will be seeing you soon. Bye.